Okay, guys. The rest of what I want you to be able to do this week is I want you to just be able to read a problem and determine what kind of what equation you're going to have to use to do it. And then we're also going to talk about the Dalton's law of partial pressure. So we're going to do both of those things on this video. Again, this video may be a little bit long. Because I just want to do several examples because there's lots of different kinds of problems here. And you have to be able to read the problem, identify what you're given, and then determine what equation it is that you need to use to solve that problem and answer that question. So let's go ahead and look at the first one here on this page. A gas occupies 3.5 liters at 2.5 millimeters mercury pressure. What is the volume at 10 millimeters of mercury at the same temperature? So we are given here 3.5 liters, which we know is a volume. We're given 2.5 millimeters of mercury, which is a pressure, it tells us, so that's a P. What is the volume? Okay, so that's what they're asking us for. At 10 millimeters of mercury, which we know obviously is going to be another pressure. And notice the temperature stays the same, so the temperature is constant. So obviously here we are not going to use the ideal gas law that we talked about in the previous videos because we would need moles, either grams or moles, and we don't have either one of those here. So we know then that we're probably going to use that combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. Now again, notice the temperature is constant. So since the temperature stays the same or is constant, we can mark that out. And then what we have left here, P1 V1 equals P2 V2, well, that's Boyle's law. Notice the directions here tell us to give the name of the gas law that's being used. So this is Boyle's law. So now we just got to figure out what are the ones and what are the twos. So the gas at this volume is this pressure. The gas occupies this volume at this pressure. So we're going to call we know these two go together. It's that volume at that pressure, so we're going to call those the ones. And then, obviously, this would be our pressure 2, and we would be solving for V2. So if we substitute our numbers in, 2.5 millimeters of mercury is the pressure, and the volume, V1, is 3.5 liters. And then P2 is 10 millimeters of mercury. And V2 is what we're solving for. So to solve for V2, you can see here that we're going to need to divide both sides by 10 millimeters of mercury. Okay, millimeters of mercury is going to cancel out.
If you have not turned your paper packet work in up front, please go ahead and make about 5 copies of each one of those and bring that to the front.
Okay. Sorry about that. I'm at school. So now we're just going to work out this left side here. 2.5 times 3.5 equals divided by 10. And I get 0.875 liters. And when I look all of my numbers here, let's go ahead and put a decimal after that so that way it has 2 significant digits. So we're going to round this to 2 significant digits, which will be 0.88 liters will be my V2. Okay? So again, the main thing, it's easy to work out the problem. The main thing here is I want us to practice identifying what we're given, what we're looking for, what we're going to be solving for, and then how to determine which equation that we need to use. Again, the 2 main equations that we have are the combined gas law that we can use to get Boyle's law, Charles' law, or Gay-Lussac's law, and then we also have the ideal gas law. So those are the main 2 that we're choosing from, just kind of like in the previous video that we just did. So let's go ahead and look at the next one here. A sample of 25 liters of NH3 gas at 10 degrees Celsius is heated at constant pressure until it fills a volume of 50 liters. What is the new temperature in degrees Celsius? So again, we have 25 liters, which we know is a V. We have 10 degrees, which we know is a T. We have 50 liters, which we know is a V, and we are solving for a new T. So that's what we're looking for. So this volume is at this temperature. So we're going to call those V1 and T1. And so then we're going to fill a new volume and we're going to look for a new temperature. So those would be V2 and T2. So again, obviously, since we're not using grams or moles here, we know we're going to need to use that ideal gas law to determine our answer. So again, P1 V1 equals over T1 equals P2 V2 over T2. Again, here we have V's and T's. It doesn't say anything, or yes, it does. It tells us that the pressure is constant. So then we mark out P, and what we have left is V1 T1 equals V2 T2, which, if you remember, that is Charles's law. It tells us that volume and temperature are directly related. As volume goes up, as temperature goes up, volume goes up. As temperature goes down, volume will go down. So all we got to do then is substitute in the numbers. 25 liters for V1. T1 is 10 degrees, but remember we do have to convert that to Kelvin. So plus 273, our T1 will be 373 K. On the right side, our V2 is 50 liters. And we're going to go ahead and put a decimal after that, so we'll have two significant digits because I don't like just having one significant digit. You guys know that. And then our T2 is what we're solving for. So again, to solve for this, we're going to do that cross multiplication since that T2 is on the bottom. So 25 liters times T2 is equal to 50 liters times 373 K. Again, to solve for T2, we're going to have to divide by 25 liters on each side. So when we do all that, T2 is going to be 50 times 373 divided by 25. And I have 746, and again, this is going to be K. I'm going to make sure 50 times 373 equals divided by 25. And let's make sure that makes sense, 746K. Well, at a volume of 25 liters, the temperature, or at a temperature of 10, the volume is 25. So then if we heat it until it is 50, obviously we're heating it, so the temperature is going up. So yes, that does make sense. Higher temperature, higher volume. So again, the last thing we need to look at is significant digits. Here we have 2. If we put a decimal after the 10, we have 2. And then we put a decimal after the 50, we also have 2. So we need 2 significant digits. So that would be these two. The 6 makes the 4 a 5. So that would be 750K would be our T2 rounded to 2 significant digits. Okay. The next one. A certain quantity of argon gas is under 16 torr pressure at 253 K in a 12-liter vessel. How many moles of argon are present? Obviously, this one is talking about moles, and so therefore we know we're going to be using that ideal gas law, PV equals nRT, where N is the number of moles, so we know we're solving for N because it's asking us how many moles. This is our P, obviously, 253K. Okay, that's our temperature, and then liters is going to be our volume. So 16 torr times a volume of 12 liters is equal to N, that's what we're solving for, times our R. Okay, which R do we use here? Well, let's go back here and look at the R's that we have. The only 2 R's that I gave you were, let me find them, right here. I gave you one in atmospheres and one in kilopascals. So therefore, what this means is that we're going to have to convert that torr. We can't just use the torr. We're going to have to convert it either to atmospheres or kilopascals. Well, if you will remember yesterday, we talked about how that 1 atmosphere is 760 millimeters of mercury and is also 760 torr. So instead of using that torr, we're actually going to have to convert that to atmospheres so that we can use the R for atmospheres. So 16 torr over 1 is our pressure. According to our problem, 16 torr is our pressure, so we want to convert that to atmospheres. So we're going to put torr on the bottom, so it'll cancel out, and we want to change that to atmospheres, and here is our conversion factor. 1 atmosphere is 760 torr. So 1 atmosphere is 760 torr. So what we're going to do here then is we're going to have 16 on the top, and we're going to have 760 on the bottom. So 16 divided by 760 gives us 0.021052 atmospheres. And again, I'm not rounding here because this is not a final answer. So rather than putting the 16 torr here, I'm not going to do that because I don't have an R that has torr in it. I have to change my torr to atmospheres so that I can use the R for atmospheres. So I'm going to substitute in here then 0.021052 atmospheres. That has to be atmospheres, okay? And so then our R, if we go back here and look, the R for that has atmospheres in it is going to be, that's kilopascals, here it is, 0.0821 liter atmosphere mole Kelvin, okay? So 0.0821 liter atmosphere mole Kelvin. Okay, and then our temperature, luckily, is already given to us in Kelvin, so we just have to substitute it in, 253K. All right, so what I'm going to do here is I'm going to go ahead, since I already have this number in my computer, I'm just going to go, or I'm sorry, in my calculator, I'm just going to go ahead and multiply here to get an answer on this side. So times 12, and so then I have 0.252631579. And that is atmospheres times liters. And then on the other side, I have N, and I'm going to multiply this out. So 0.0821 times 253 gives me 20.7713, and that is liter atmosphere over mole Kelvin. And then we're going to have to, obviously, to solve for N, we're going to have to divide both sides by 20.7713 liter atmosphere mole Kelvin, and do the same thing over here, 20.7713 liter atmosphere over mole Kelvin. So all of this will cancel out, and on the right we will have N, and on the left we're going to do our 0.252631579 divided by 20.7713, and then I get 0.012162531. And again, atmospheres and liters divide out. The Kelvin's already gone. I'm sorry, it canceled out over here when we multiplied by the 253 Kelvin. And then the liter atmosphere cancels out, and what I have left is moles. So this is moles. And again, looking at significant digits, we have 2, 3, 2. So we need 2. So these 2 would be my 2 significant digits. Remember, zeros at the beginning do not count as significant. This one does not change that 2, so my final answer is 0.012 moles would be my N. I'm sorry, this is the answer right here. Okay? Moving on, one more on this page. If 11 moles of HCl gas occupies 15 liters at 300 degrees Celsius, what is the pressure in torr? Okay, so I have 11 moles. Obviously, this is moles, so I'm going to be using the ideal gas law. Again, moles is my N. 15 liters, that's my V. 300 Celsius is my T, and I'm solving for my P. Okay, now our T is going to have to be converted to Kelvin, so we're going to add 273 to that. So 300 plus 273 is going to be 573K. And I'm just going to do it up here because I'm not doing these other two problems. PV equals nRT. Our P is what we don't know. Our V is 15 liters. Our N is 11 moles. Our R, okay, our R, again, we know we have one with atmospheres and one in kilopascals. Neither of those has a torr. But if you remember what we did earlier, we converted torr to atmospheres. So I can use the R that has atmospheres in it, and then when I get my answer, I can do just like this and convert it to torr. So that's what we'll do, since the question is specifically asking us for the pressure in torr. So we'll go ahead and use the R that has atmospheres in it because I know the relationship between atmospheres and torr. So That is 0.0821 liter atmosphere over mole Kelvin. And then our temperature is 573 K. Okay, so our K's will cancel out. And in order to solve for, and also our moles will cancel out, sorry. And in order to solve for P, we're going to have to divide both sides by 15 liters. So that cancels out. Liters will cancel out, and we will be left with atmosphere. So pressure is equal to 11 times 0.0821 equals, divided by 15 equals. And I get 0.060206667, and that's atmospheres. Now, if I could leave my pressure in atmospheres, I would be done right there. But since it is asking me for torr, the pressure in torr, we're going to use that relationship. 1 atmosphere is 760 torr. So I'm going to take my P, which is 0.060206667 atmospheres. I'm going to put it over 1. And then I know atmospheres is going to go on the bottom, so it'll cancel out. Torr will go on the top. And again, remember our relationship, 1 atmosphere is 760 torr. So 1 atmosphere is 760 torr. So what I'm going to do here then is I'm going to multiply my 0.060206667 times 760. And when I do that, I get 45.7570667 torr. Now I have to look at significant digits. 11 has 2, 15 has 2. Let's go ahead and put a decimal there and say that 300 has 3. So we're going to do 2 significant digits, which would be the 4 and the 5. The 7 does make the 5 round up to a 6. So that would be 46 torr with 2 significant digits. And that will be our pressure in torr. Okay? So again, just a little bit of practice, being able to read that problem, identify what you're given, what variables you have been given, identify what variable they're asking you to solve for, and then determining which equation that we're going to use to solve for that. Again, for these last two that we've done, we use the ideal gas law here, and we use the ideal gas law on this one. We always know we're going to use the ideal gas law if it starts talking about moles or grams, because if it gives us grams, we can convert grams to moles, and so then we would have moles and we could use the ideal gas law. All right, moving on then, let's talk about Dalton's law of partial pressure. And I have that a little bit on your PowerPoint online about this. Dalton's law of partial pressure says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. So again, the total pressure, PT, is equal to the sum of the partial pressures. So the pressure of gas 1, pressure of gas 2, pressure of gas 3, so on and so forth. So that is relatively easy to understand and simple. We also have to understand, however, that since the pressure of any gas is proportional to the number of moles of the gas, we're going to be using that relationship as well. So the pressure is proportional to the number of moles. So if we know that the pressure is proportional to the number of moles, if the volume remains constant, then the partial pressure of any gas in the mixture is proportional to its percentage. So we can actually take percentages and figure out, if we know the total pressure in the container, and we know that 20% of the gas in that container is oxygen, and 20% is nitrogen, and 15% is hydrogen, and so on, we can take those percentages and help us to determine what the partial pressure of each gas in the container is. Another thing that we can do, if we know the number of moles, then we can take the number of moles of each gas in the container, divide that by the total number of moles in the container, which gives us a percentage, and then again, we can use that percentage to help us calculate the pressure of each gas in the container if we know the total pressure in the container. And I know that kind of sounds a little bit difficult. Maybe it's not difficult at all. Basically, you're just using ratios here, proportions. It's not too difficult, especially if you're good at math or you like math. But anyway, we are going to do some example problems to kind of help you understand what I'm talking about here. So let's go back to our handout. And again, so this is our law. The total pressure is equal to the sum of the partial pressures. So the first couple of problems that we do, we're just going to use that. So we're going to look first at number 1 here. A container holds 3 different gases. The partial pressures are 25 kPa, 42 kPa, and 63 kPa. Find the total pressure. Well, obviously, the total pressure is equal to the sum of the partial pressures of each gas. It doesn't matter if you use ABC or 1, 2, 3. So obviously, according to Dalton's law of partial pressure, we can take the partial pressure of each gas in the container and add it together to find the pressure of all of the total pressure in the container. So gas 1, we're going to say that pressure is 25 kPa. Gas 2, 42 kPa. And gas 3, 63 kPa. So when we add all those together, 25 plus 42 plus 63, we get that the total pressure in that container is 130 kPa. And again, 2 significant digits in all of our measurements in the problem, so 130 does have 2 significant digits. So that's really simple. Moving on to another one. And again, I'm doing these on another piece of paper because we don't have a lot of room here on our actual handout. A tank holds 2 gases. The total pressure is 150 atmospheres. Notice the 150 does have a decimal after it. If the partial pressure of one of the gases is 35 atmospheres, find the pressure of the other gas. So here we know that PT, or total pressure, is 150. We know that the pressure of one gas is 35 atmospheres, so we want to know the pressure of the other gas, which is P2. So, again, PT is equal here to the pressure of the 2 gases added together. So, if the total pressure is 150 and the pressure of the first gas is 35, then we want to know what P2 is. So, again, obviously, we're going to subtract. Again, I know you knew how to do this by just reading it. But however, I wanted to go ahead and work it out algebraically because I think we need a little bit of practice doing our algebra. So 150 minus 35, I think is 115. Yes, 115 atmospheres. Okay, and even though 35 has 2 significant digits, I'm going to go ahead and put 35.0. That way we can leave the 115 atmospheres as our answer because I would hate to round that up to 120 because 120 and 35 doesn't add up to be 150. So. Or I'm sorry, 120 and 30 doesn't add up to be 150. Okay, moving on. Looking at the next one. Okay, this is where we're going to get into our proportions. And looking at percentages. A tank contains 32 moles of N2 gas and has a pressure of 8 atmospheres. If 4 moles of Ne are added, find the new pressure. All right, well, no, I'm not going to do that one. I'm going to go ahead and skip all that one because I want to use the percentages. Number 6. The percentages of the 2 major gaseous components of air are 21% oxygen and 78% nitrogen. The remaining 1% is mostly CO2 and argon. The total pressure is 101.3 kPa. Find the partial pressures of oxygen and nitrogen. Okay, well, we know that 1% of air is oxygen and nitrogen, and the total air pressure around us is 101.3 kPa. So, if 1% of the mixture is CO2 and argon, then we know that we can take, and 21% of it is air, or is oxygen, I'm sorry, then we can take 21% of that 20% of that 101.3 kPa to get the partial pressure of oxygen. So if the oxygen is 21%, then as a decimal, that's 0.21, okay? We can take that times the total pressure, and that will give us the partial pressure of the O2. Okay, so 0.21 times the total pressure, which is 101.3, is going to give us the pressure of the O2. Okay, so 0.21 times 101.3 gives us 21.273. And we're going to use, let's go ahead and use just 2 significant digits here since this one has 2. So the pressure of O2, we're going to say is 21 kPa. Okay, so again, you just take the percentage, whatever percentage of the gas is oxygen, well then that percentage of the pressure is due to oxygen because it's proportional. when you're looking at the number, since the pressure is proportional to the number of moles, then we can take the percentages. The percentage of the total pressure to find the partial pressures of each gas in the container. Okay, so now we have nitrogen is 78%. So again, if nitrogen is 78%, as a decimal, that's 0.78. Again, times the total pressure is going to be the pressure of the nitrogen. So then, the total pressure, again, is 101.3 kPAs. So we just do 0.78 times 101.3. And that gives us, and if we're doing two significant digits, 79 kPAs is going to be the partial pressure of the nitrogen. So again, if you know the percentage and you know the total pressure, then you can determine the pressure of each gas in the mixture in that container. Okay, moving on to another one. Let's look at this one. Just another example on a different page. And this one actually has room so I can work it on here, I think. It says if 7.10 grams of CO2 gas, 3.00 grams of HE gas, and 2.00 grams of H2 gas are placed in the same container at a total pressure of 101.3 kPa, what is the partial pressure of each gas? Okay, notice we don't have percentages here, guys. So we're going to have to determine the percentages. However, we can't determine the percentages by looking at the number of grams because it's not the number of grams that are proportional. It's the number of moles. So the first thing we're going to have to do is convert this to moles, and then using the number of moles, we can determine the percentages and then take those percentages of that total pressure to get the partial pressure of each one of these gases. So again, we're going to convert grams to moles. So we're going to take 7.10 grams of CO2. We're going to take 3 grams of helium, and we're going to take 2 grams of hydrogen. Okay, and then Cl is 35.5, so 2 Cls is 71.0 in 1 mole. He is 4 grams in 1 mole, and again, we're getting that from the periodic table. And then hydrogen, H2, is going to be 2 because each hydrogen is 1 gram in 1 mole. Okay? That doesn't cancel out. All right, so in the first one, 7.1 divided by 71 gives us 0.1 moles of Cl2. 3 divided by 4 gives us 0.75 moles of He. And then 2 divided by 2 gives us 1 mole of H2. So now what we need to do is find our total number of moles and then use that to determine the percentage of each gas in this mixture. So we have the total number of moles is 0.1. Let's go ahead and do this. Total moles is equal to 0.1 plus 0.75 plus 1. So 0.1 plus 0.75 plus 1 gives us 1.85 moles of gas. Okay, so to get our percentages, we're going to divide each one of these by 1.85. So 1.85. Again, we're just taking the part divided by the total, the part divided by the whole. That's how you do percentages. Anytime you want a percentage. Okay, so 0.1 divided by 1.85 is going to give us, and I'm just going to do like maybe 3 significant digits here, not because I have 3 in all of my, the least number I have here is 3, so 0.0541, and that is, and this is the percentage as a decimal, guys. We would multiply it by 100 to get our actual percentage, but we're just going to do it as a we're going to leave it as a decimal because we're going to need that anyway. So that is for Cl2. And then 0.75 divided by 1.85 gives us 0.405, and that's for He. And then 1 divided by 1.85 equals and that gives us 0.541 because I got 0.5405, so 0.541. Now, those are our percentages as decimals, all right? So now we can take those percentages times the total pressure to get the partial pressure of each gas. So times the 101.3 for each one. Okay, so 0.541 times 101.3 gives me, and again, I'm going to do 3 significant digits, so 54.8 kPa for H2. 0.405 times 101.3 gives me 41.0 kPa for the HE, and then 0.0541 times 101.3 gives me 5.48 kPa for the Cl2. So these are the partial pressures for each one of those gases. And then to check ourselves, we can add all these up to make sure they add up to 101.3 or somewhere very close. 5.48 plus 41 plus 54.8 gives me 101.28, which is 101.3. So, again, if you're given grams, grams are not proportional. Okay, it has to be the moles. So we have to convert the grams to moles. Once we do that, we find the total number of moles and then divide each number of moles by that total to get the percentage as a decimal of each gas in that mixture, and then we just multiply that percentage times the 101.3, the total pressure, to get the partial pressure of each gas. Because again, as we said earlier, the partial pressure of each gas is proportional to the number of moles as a percentage of that gas in that mixture. Okay? And one more that we're going to look at here before I give you some problems to do. If oxygen molecules make up 20.5% of the molecules in the atmosphere, what is the partial pressure of oxygen at sea level if the total pressure of the atmosphere at sea level is 14.7? So again, this is the percentage that is oxygen. So I could take that percentage as a decimal, times it times the total pressure, and that will give me the partial pressure of oxygen. So 0.205 times 14.7 PSI. Again, you guys, PSI is just a different unit of pressure, okay? Torr is a unit of pressure. Millimeters of mercury is a unit of pressure. Atmospheres is a unit of pressure. Kilopascals is a unit of pressure. And now we have PSI, which you guys probably know is pounds per square inch. So again, lots of different units of pressure. But again, this is a percentage of this total. And so we're just going to get our partial pressure here for oxygen in PSI rather than atmospheres, torrs, millimeters, mercury, or kPas. So 0.205 times 14.7. That gives us, again, we got 3 significant digits here, so 3.01 PSI would be the partial pressure of the oxygen. Very simple. Again, you know, if you're not given the percentages, if you are given the percentages, multiply the percentage as a decimal times the total pressure. If you're not given the percentages, like we weren't in the problem that we just did a second ago, then you're going to have to change the grams to moles. If you're already given moles, guys, all you got to do is take the number of moles of the gas divided by the total number of moles to get your percentage as a decimal. But since we weren't given the percentages here we had to find the number of moles and then find our percentages and then multiply them times the total pressure. In the other one that we did a while ago, we were given the percentages. Okay, we were given the percentages, so we just turned those to decimals. If we were given the moles, again, we could find the percentages very easily. If you were given the number of moles, which I think I have a sample problem that I'll give you to do that gives you the number of moles, then you're basically starting right here. Okay, you already are given the number of moles. You would add to get your total number of moles, take each number, divide by the total, get your percentage as a decimal, and then multiply times the total pressure. So I'm going to give you a few more example problems to do. And you guys, I did change the due dates because Miss Emberton said we were going to have work done on Monday or due on Mondays. and I had your work due by Friday evening. So instead of saying, okay, due on Monday, if it's a student who doesn't have internet and is having to do pencil paper, then it's going to be due on Monday. But online, I'm having it due by Sunday evening at 11:55. So the assignment that I'm going to give you to do over this video is going to be due by Sunday evening at 11:55. Please email me if you have any questions, and if we can't answer them in an email, then I'll just ask for your number and I'll call you or FaceTime you or something. So I hope you have a good rest of your week and weekend, and we'll talk to you soon, hopefully. Bye-bye.